know, it's kind of hard for me to see what that says. Can you read that? Quiz, all right, pop quiz. Or rather, a learning outcome mastery diagnostic self-check, a chance for you to diagnose yourself to see if you've mastered the learning outcomes that we've been covering. And so the first part of this paper, which comes from ACE Physics Syllabus Code 9702, paper 22 from October-November 2014, question 6, part A here is designed to sort of assess your mastery of one of the learning outcomes that we've already studied. That learning outcome is to describe the motion of a transverse and longitudinal wave. I'll go on to work through part B here as a worked example for one of the more recently introduced learning objectives to solve problems involving two-slit and multiple slit interference. State one difference and one similarity between longitudinal and transverse waves. Take a moment, pause the video if you need to, and put your thoughts to paper based on everything that you've been studying about the motion of transverse and longitudinal waves. All right, hopefully you said something like, well, a similarity between them is that they're both waves, and waves transfer energy, right? Hopefully this construction paper vector here looks familiar to you. If not, and you had trouble with this question, maybe go back and take a look at the video that I uploaded that specifically addressed that particular learning outcome. So when the particles of the medium through which that energy is propagating are moving parallel to that direction of energy transfer, they're moving along the same direction as the energy propagation, we call that a longitudinal wave. If, however, the direction of energy transfer is perpendicular to the direction that the particles are moving, well, then that's what we call a transverse wave. That really is the key difference between them, is how the particles move in each of the types of waves. But they are both waves, and waves carry energy, and so that's a similarity. If you said something to that effect, feel good about giving yourself 2 marks on that question. Part B. A laser is placed in front of 2 slits as shown in figure 6.1. Now you can see I've already written out the relevant equation. As soon as we know that it's 2 slit interference, the relevant equation is lambda equals ax over d. The question reads, or goes on to state, the laser emits light of wavelength 6.3 by 10 to the negative 7 meters. And I've written that wavelength here above the laser. And so this laser is going to be shining light to this partition, which has 2 slits in it. It says the distance from the slits to the screen is 2.5 meters. That's the value d. The separation of the slits is 0.35 millimeters, and that's what we call A. An interference pattern of maxima and minima is observed on the screen. Explain why an interference pattern is observed on the screen. For light, maxima are points of brightness, and those are points of reinforcement of the waves. For light, points of minima are dark spots. Okay, if it were sound, maxima would be loudness, minima would be quiet. If it were water waves that were interfering, then the points of maxima would be sort of the most displacement or the most splashing, and the minima would be points where there's not so much splashing at all. And again, it's always for the same reason, that the coherent waves are meeting and they are reinforcing for maxima and canceling for minima. If we consider this point directly in the middle of the 2 slits and across from them at the distance, d here on the screen, then we know both of the light waves that emerged from these slits had to travel the same distance to get there. And so their path difference is going to be 0. When the path difference is 0 times the wavelength, or 1 times the wavelength, or 2 times the wavelength, or any integer times the wavelength, then crest is going to meet crest, and we will observe a point of maxima there. We could also explain that in terms of the phase difference. And so one wave we could kind of think about is like 360 degrees or 2 pi radians. And so the phase of the wave is just sort of like where in that oscillation is it. And so here would be like 90 degrees of phase, 180 degrees of phase is halfway, 270 degrees of phase would be at this point, and then 360 degrees is sort of the entire wave. 90 degrees, 180, 270, 360. So that's sort of like the phase of the wave. Now, if the phase difference is 0, then the light is going to meet crest to crest and we'll observe a point of maxima. Because the light has traveled the same distance, we kind of know that that's true here. But let's suppose we move off of that point just a bit here. Well, now the wave from this bottom slit has had to travel a little bit further than the wave from the top slit. And so when the crest of this wave reaches here, it will meet the trough of the wave that's coming from the bottom slit because it's had to go an extra half of a wavelength. And so when the path difference is a half of a wavelength, or 1.5 times the wavelength, or 2.5 or 3.5, then that's where we'll observe destructive interference and points of darkness, or minima. And we'll continue to observe that because here would be sort of the point where this one's had to go an extra half a wavelength. Above that, we'd observe another point of maxima because now the wave has still had to travel longer, but it's had to go a whole extra wavelength. And so once again, the crest from this wave will meet the crest from this wave, and we'll see a point of maxima, or brightness. So these alternating points of maxima and minima are what characterize an interference pattern. And one of the things that we must have in order to get that interference pattern is a coherent source of waves. By using a single laser, then sending it through two slits, we're ensuring that the light from the laser is coherent and will indeed interfere. So coherence is when the frequency of the waves is constant and remains constant over time. They have the same frequency. If one of the waves had a different frequency and therefore different wavelengths, then the waves would sort of move in and out of phase with each other. And so in order to observe interference, a coherent source of waves must meet, and we're observing where they're meeting here at the screen 2.5 meters away. I'll leave it to you to kind of put that into your own words. Calculate the distance between adjacent maxima is the next question here. The distance between adjacent maxima is what we call x in this equation. And so we can solve this using the equation lambda equals ax over d, reorganizing it by multiplying both sides by d over a. We can get x as the subject, and it will equal d times lambda over a. Substituting in values, we've got the distance, 2.5 meters. We've got the wavelength, 6.3 by 10 to the negative 7 meters. And remember, we must convert A from millimeters to meters. And so milli is the same thing as 10 to the negative 3 meters. And while that's not technically correct scientific notation, where we kind of want the decimal point to be here, your calculator doesn't mind, and it will still be able to solve that. 2.5 meters times the wavelength, 6.3 by 10 to the negative 7. That's our numerator, divided by, and always remember to use grouping symbols when you're dividing by something in scientific notation. Your calculator will rigidly follow the order of operations, and it will divide by this and then multiply by that when we want to divide by that entire quantity. And so we'll use grouping symbols to give the calculator the language that it understands. And we get 0.0045 meters, or 4.5 by 10 to the negative 3 meters. That would be how far apart these bright spots would be over here. And again, those bright spots are due to a path difference, that is some integer times the wavelength. And so here is, there is no path difference. The path difference is 0. Here it's a whole 1 extra wavelength. If we were to go up to the next maxima, then this wave would have had to travel 2 extra wavelengths, but it's 2 times the wavelength, or 1 times the wavelength, or 0 times the wavelength. For the points of minima, remember, that's when one of the waves has had to travel an extra half of a wavelength, and so the path difference will be half of a wavelength, or 1.5 wavelengths, or 2.5, and so on. The phase difference could be thought in terms of either degrees, and so some integer times 360 degrees to get points of maxima, or some integer times 180 degrees to get some points of minima, right? Where the phase difference is off by 180 degrees, and so a crest will meet a trough and destructively interfere. State and explain the effect, if any, on the distance between adjacent maxima when the laser is replaced by another laser emitting ultraviolet radiation. In order to correctly answer this question, you have to remember that the wavelength here is in the visible part of the spectrum, be like orange light, an orange laser. Here, ultraviolet radiation has a shorter wavelength than even violet light, and violet has the shortest wavelength of all the visible part of the spectrum. And so anchor your thoughts, to the equation here that sort of governs this. The wavelength is equal to AX over D. It's asking about how will the value x change as we change the wavelength. So if we don't change the separation of the slits A and we don't change the distance D from the slits to the screen, then as we make the wavelength shorter, so too must the distance between adjacent maxima decrease. I'll leave it to you again to put that into your own words there, but always try to anchor your thoughts to an equation when and where you can in physics.